Welcome to another edition of Audio Notebook. I want you to start by picturing something we've probably all done at least once in our lives.
Oh, definitely.
You step outside on a really clear, dark night. Maybe you're out in the country, miles away from all that awful city light pollution.
Right, where you can actually see the sky.
Exactly. And you look up and you see that massive, just glittering dusting of stars scattered across the absolute blackness.
It's a pretty awe-inspiring sight.
It really is.
Yeah.
And if you're anything like me, you get that feeling, that
Yeah.
profound, almost dizzying sense of scale.
Yeah, you look at those billions of points of light and your brain just kind of assumes things.
Right. You feel the sheer weight of the assumption that, well, we cannot possibly be alone. I mean, the universe is just too big.
It feels like it has to be crowded, right? With alien civilizations, bustling intergalactic empires, or at least like a few noisy neighbors broadcasting radio waves out into the void.
Exactly. It's arguably the most intuitive feeling a human being can have.
It really is. You look at the astronomical numbers, you look at the physical size of the sky, and your brain immediately populates the darkness.
Because you assume that if it happened here on this random rock, it has to be happening everywhere.
Right, and that is exactly the feeling our mission for this edition of Audio Notebook is going to fundamentally deconstruct.
Yeah, we are going to completely upend how you think about your place in the cosmos.
We really are. To do this, we've been digging through a massive stack of recent astrobiology papers, planetary formation simulations, all the latest astronomical data.
We're going to dive into the, I'd call terrifyingly beautiful math and the hyperspecific chemistry and planetary mechanics.
Stuff that suggests our world might not be a typical run-of-the-mill rock at all.
Right. Instead, Earth might be a profound cosmic anomaly, like an actual statistical impossibility.
Which brings us right to the doorstep of the famous Fermi paradox.
Oh, yes.
Yeah.
Enrico Fermi.
Yeah, back in the mid-20th century, the physicist Enrico Fermi was looking at all those stars, did some quick mental math on the age of the universe, and asked a very simple, very chilling question.
Where is everybody?
Exactly. If the universe is so incredibly vast and it's been around for nearly 14 billion years, any civilization with even a slight evolutionary head start on us should have colonized the galaxy by now.
We should see the megastructures.
We should hear the radio chatter. We should see the cosmic equivalent of city lights.
But when we point our telescopes and listen, we hear absolutely nothing.
Just the great silence.
And that silence clashes violently with the scientific philosophy we call the Copernican principle, or the principle of mediocrity.
Let's unpack the history of this for a second. Because for centuries, really ever since Nicholas Copernicus proved that the Earth revolves around the sun and not the other way around, science has operated on a core assumption.
Which is that there is absolutely nothing special about Earth.
Right. We're supposedly just a totally average rocky ball orbiting a completely standard, boring star.
Tucked away in a deeply unremarkable, run-of-the-mill spiral galaxy.
And if we are mediocre, the logic naturally follows that the biology that happened here should be absolutely everywhere.
I mean, the historical bias driving that assumption is massive, right?
Oh, huge. Every single time humanity thought we were special or central to the universe, science came along and proved us wrong.
We thought we were the center of the solar system. We weren't.
We thought our sun was the center of the galaxy. It wasn't.
Our galaxy isn't even the center of the universe.
So astrobiologists and astronomers naturally assumed that our biology wasn't special either. This led to decades of science fiction and scientific optimism predicting a galaxy bursting with life.
But then, right around the year 2000, there was a massive paradigm shift in how we viewed our own origins.
Yeah, paleontologist Peter Ward and astronomer Donald Brownlee put forward a revolutionary framework known as the rare earth hypothesis.
They essentially looked at the scientific community and said, hold on, we are conflating two entirely different things here.
This is a crucial distinction that often gets lost in popular science. The rare earth framework does not argue that all life is rare.
Right, it doesn't say the universe is completely dead.
Exactly. In fact, the simplest forms of life, single-celled organisms, microbes, basic bacteria, might be incredibly common throughout the cosmos.
Because we find extremophiles right here on Earth living in insane conditions. Boiling hydrothermal vents at the bottom of the ocean.
Highly acidic caves buried under miles of glacial ice.
Life, at its most basic, foundational chemical level, is incredibly tenacious.
I always think of it like finding mold in a damp basement.
Oh, well, that's a great analogy.
If you leave a wet piece of bread down there, you are going to get mold. The universe is probably full of cosmic mold. Finding basic chemical life might be a given.
But finding a fully functioning, climate-controlled, exquisitely maintained botanical garden down in that dark basement.
Yeah, that requires a miracle.
And that's the difference between microbes and metazoans.
Yeah.
Multicellular animals, higher plants, and eventually human-level intelligence.
Because metazoans are staggeringly fragile. A microbe can go dormant for millions of years. It can survive being frozen solid in a comet.
Or survive massive doses of radiation.
Right. But a complex ecosystem. Think about a biosphere with mammals, complex food webs, migrating birds. That requires absolute unbroken environmental stability.
And providing that level of continuous stability requires an improbable, almost absurd combination of planetary events.
So what does this actually mean for how we search for life? Because usually, the moment astronomers find a new exoplanet, the media asks exactly one question.
Let me guess. Is it in the Goldilocks zone?
Exactly. The circumstellar habitable zone, the Goldilocks zone.
The idea being that the planet is not too hot, so the water doesn't boil away into steam, and it's not too cold, so the oceans don't freeze solid.
Right. It's that orbital band where liquid water can exist on the surface.
It's a fantastic PR term for space exploration agencies looking for funding, honestly.
It really is. But astrobiologists are increasingly saying it's a massive oversimplification of what habitability actually requires.
A radical oversimplification, right?
Yeah. Serious astrobiologists cringe a bit at the mainstream obsession with just the standard Goldilocks zone. Liquid water is absolutely necessary, without question.
It's the ultimate universal solvent for carbon-based chemistry.
You need a liquid medium for molecules to bump into each other, share electrons, form those complex structures required for life.
But having water is merely buying the entry ticket to the cosmic lottery.
Yeah, it is far from holding a winning ticket. Because just being the right distance from the sun on day one doesn't guarantee you can actually keep that water over the vast scales of geological time.
And this introduces, well, maybe the most terrifying dimension of the rare earth argument, the dimension of time.
Specifically, we need to talk about the continuously habitable zone.
Because stars aren't static, right? They aren't unchanging light bulbs hanging in the sky.
Exactly. They're dynamic nuclear furnaces, and they evolve. Our sun is a G-type main sequence star. Over the billions of years since it formed, as it fuses hydrogen into helium in its core, the core becomes denser and hotter.
Meaning the sun has actually grown roughly 30% more luminous since the Earth was formed.
Right.
Wait, hold on. So the habitable zone actually moves.
It does.
I always pictured it as a permanent painted ring around the star that just stays there forever.
No, it's constantly shifting. As a star ages and burns hotter and brighter, the physical boundaries of the habitable zone are continuously pushed outward into the solar system.
So a planet might form in the absolute perfect spot. It's got oceans, it's got a great climate.
But 2 billion years later, the star heats up. The inner edge of the habitable zone shifts past the planet,
And suddenly those oceans start to evaporate.
triggering a runaway greenhouse effect until the entire world boils dry, which is likely exactly what happened to Venus.
Wow. So Venus is the perfect cautionary tale here.
Absolutely. To support the evolution of complex metazoan life, a planet doesn't just need to be in the habitable zone today.
It needs to have been in the habitable zone uninterrupted for billions of years while the star itself is changing.
Think about the sheer scale of the evolutionary marathon here on Earth. It took nearly 4 billion years for complex multicellular life to really emerge and take hold in a meaningful way.
4 billion years. That number is so big it almost loses its meaning.
It really does.
But think about it this way to the listener. That is almost 90% of Earth's entire existence. For 9 out of 10 days this planet has existed, it was basically just a rock covered in microbial slime.
The fragility of that timeline is stark. If a planet's environment fails at any single point during that 4 billion year chain,
See, if the oceans freeze over entirely into a snowball Earth that it can't escape from,
or if the atmosphere enters a runaway greenhouse effect even for a few million years, the chain of biological complexity breaks.
the evolutionary clock just resets.
Yeah, the metazoans die off, the planet reverts to a microbial state, or it becomes completely sterile. Earth's defining, perhaps most miraculous feature isn't just that it has liquid water.
It's unbroken, uninterrupted stability through deep, deep time.
Exactly. And to survive a 4 billion year marathon without tripping once, you need a perfect track.
Let's break down the actual physical prerequisites for this level of stability. What does a planet mechanically need to maintain that kind of environment?
Because we have this list of 9 overlapping planetary conditions, and honestly, Each one is wilder and less likely than the last.
Let's start with our orbit. It's incredibly boring.
Boring is exactly the characteristic you want if you're trying to evolve a delicate nervous system over 1 billion years.
I suppose that makes sense.
Yeah, Earth orbit is nearly circular. It gives us a consistent, steady, reliable influx of solar energy year-round.
And when we point our telescopes out at exoplanets and other star systems, we don't always see that, do we?
Not at all. We see a disturbing number of highly eccentric, elongated orbits. These are planets whose orbits swing wildly close to their star, getting scorched, and then fling way out into the freezing dark of the outer system.
Imagine trying to evolve complex biology when every single summer literally boils the surface oceans.
And every winter freezes the entire atmosphere solid, so the gases fall to the ground as snow.
You simply can't adapt to that level of chaos. We sit safely in the middle range of the sun zone, with an orbit that keeps our energy budget remarkably flat.
But an orbit is just the beginning of the gauntlet. You mentioned water earlier. Here is an absolutely fascinating quirk of our solar system.
Oh, I know this one. Earth likely formed completely dry.
Yes. In the violent, fiery accretion disk of the early solar system, the inner region where Earth was coalescing was simply too hot for water to condense into ice or liquid.
We were formed as a sphere of molten glowing rock.
Which means the fact that we currently have these vast, incredibly deep oceans covering 70% of our surface is almost unreasonable.
If we formed dry, where did all this water come from?
The prevailing astrological models suggest it had to be delivered later. During the planet's cooling phase, we were subjected to an incredibly lucky barrage of water-rich asteroids and comets from the outer solar system.
From out beyond the frost line where water could naturally freeze.
Right. Some models even suggest a singular, massive planetary collision delivered a huge payload of ice.
Regardless of the exact delivery mechanism, the sheer volume of water we ended up with is a critical life support mechanism. Deep oceans aren't just swimming pools for fish to evolve in.
No, they are massive planetary thermal buffers. That massive volume of water is doing a lot of heavy lifting.
Because water has an incredibly high specific heat capacity, meaning it takes a lot of energy to change its temperature.
Exactly. It absorbs heat from the sun very slowly during the day and releases it very slowly at night. This acts as a global shock absorber for our climate.
Without deep oceans continuously transferring heat from the equator to the poles via ocean currents, the temperature gradients on Earth's surface would be incredibly harsh.
Right. Unlivable. We'd be looking at hyperhurricanes, massive dead zones, and fundamentally uninhabitable temperature extremes.
Okay, so we have a wonderfully boring orbit, and we received a highly improbable late delivery of deep oceans. Now let's talk about the sky, specifically the moon.
Ah, the moon.
Because I think humanity takes the moon for granted. It's just up there, glowing, changing phases, pulling the tides. But the actual origin story of our moon is violently unique.
We call it the giant impact hypothesis, or the Theia collision. Very early in Earth's history, a Mars-sized protoplanet, which scientists have named Theia, was on a collision course with us.
And it smashed into the early Earth with an unimaginably powerful, glancing blow.
The impact was so energetic it completely liquefied Earth's surface again and blasted a massive ring of vaporized rock and debris out into orbit.
And over time, that debris ring coalesced and cooled to form the moon.
Exactly. And the result of that cosmic hit and run is that our moon is anomalously large compared to the size of Earth.
Right, because in our solar system, moons are usually tiny specks compared to their host planets, like the little asteroids orbiting Mars, where they orbit massive gas giants.
We essentially live in a binary planetary system, and that unusually large companion acts as an incredible gravitational anchor.
It stabilizes Earth's axial tilt, which astronomers call our obliquity.
Yes. Earth tilts at about 23.5 degrees relative to our orbit, which is what gives us our mild, predictable seasons.
If we did not have that massive moon anchoring our tilt, the gravitational tugs from other planets, especially Jupiter, and the sun would cause Earth's axis to wander wildly over millions of years.
We could tilt all the way over on our side, like the planet Uranus.
That would mean one hemisphere points directly at the sun for months on end, baking under continuous brutal daylight.
While the other hemisphere freezes in total, unending darkness.
Once again, it's a chaotic climate shift that would act as a kill switch for any complex evolutionary chains.
And recent planetary formation simulations have added a fascinating new layer to this. They've revealed a very tight physical constraint on the formation of these large, stabilizing moons.
Oh, really? What kind of constraint?
It turns out planets that are significantly larger than Earth, say, super-Earths that are over 6 Earth masses, actually cannot form fractionally large moons like ours, even if they get hit by a protoplanet.
Wait, why wouldn't a bigger collision just make a bigger moon?
Because of the thermodynamics of the debris disk, when a massive planet suffers a giant impact, the debris disk it generates is incredibly dense and vapor-rich.
And the gravity of the large planet holds onto that vapor tightly.
Exactly. The gas drag inside that disk becomes so high that any small moonlets that try to condense and orbit simply lose their momentum.
Oh, I see. The friction of the gas slows them down.
And their orbits decay until they fall right back into the planet. So you need a planet exactly the right size to get hit by exactly the right sized object at exactly the right angle to form exactly the right sized moon to keep your climate stable for 4 billion years.
That is absurd. And we haven't even talked about the inside of the Earth yet.
The internal planetary engines.
Because we look at a globe, we see mountains and oceans, but we forget the planet is a giant machine. Let's move inward and look at the magnetic shield.
The geodynamo. If a planet does not have this, almost everything else we've talked about is completely moot.
So deep inside the Earth, we have a solid inner core made of crystallized iron and nickel, surrounded by a churning liquid outer core of the same metals.
And the rotation of the Earth creates a Coriolis effect within that molten metal.
Okay, I've heard the term dynamo before, but let's break that down for someone who isn't a geophysicist. How does a ball of spinning liquid metal actually create a magnetic force field that extends thousands of miles into space?
Think of the liquid outer core like a boiling pot of water, but instead of water, it's highly conductive molten iron. The heat from the inner core causes the liquid metal to rise, cool, and sink back down. That's convection.
And because the Earth is spinning, those rising and falling columns of liquid metal are twisted into spirals.
Exactly. Moving a conductive fluid creates electrical currents. Those massive electrical currents, in turn, generate a magnetic field.
It becomes a self-sustaining electromagnet, powering an invisible shield that deflects incoming radiation.
Without it, we wouldn't just get a bad sunburn. The surface of the planet would be sterilized.
The solar wind, which is a relentless stream of highly charged lethal particles blasting out from the sun at incredible speeds, would hit our atmosphere directly.
Over geological time, the solar wind would physically strip our atmosphere away into space, molecule by molecule.
It would also allow high-energy cosmic rays to bombard the surface, systematically shredding the DNA of anything trying to crawl out of the primordial mud.
And to maintain that geodynamo, the planet must hold on to its internal heat for billions of years. Mars is the tragic counterexample here.
Because it's much smaller than Earth, so it had a higher surface area to volume ratio. It cooled down much faster.
Right. Its liquid core solidified, the convection stopped, the magnetic field shut off, and the solar wind systematically stripped away its once thick atmosphere,
turning it into the frozen, irradiated desert we see today.
That brings up a great point about gravity and the sheer size of a planet.
Yeah, I was reading a 2017 statistical study that looked at rocky exoplanets between 1 and 100 Earth masses. They found that surface gravity across those planets is often surprisingly similar to Earth's.
Because as a planet's mass increases, its radius also increases, so the surface gravity scales in a way that stays somewhat in the same ballpark.
So someone could easily look at that and say, hey, Earth-like gravity is actually super common.
It is a totally fair observation, but it misses a critical biological nuance. While gravity within a tolerable range might be common, Earth sits in a highly specific sweet spot.
Right. If the gravity were significantly higher, say, on a large super-Earth, the atmosphere would be pulled down so tightly it would become crushingly dense.
And land-based biology would struggle immensely with structural integrity. Think about the energy required just to pump blood up a giraffe's neck here on Earth.
Scale the gravity up, and complex, large-bodied circulatory systems fail.
Beyond just biology, doesn't too much mass mess with the geology, too?
Drastically. If the planet is too massive, it attracts too much gas during its initial formation and simply becomes a gas giant like Neptune.
Or if it accumulates too much water, it becomes a deep ocean world.
And the water pressure at the bottom of those oceans would be so immense that the water would compress into exotic, high-pressure phases of solid ice, like Ice the Seven.
And that layer of exotic ice would completely seal off the liquid water from the rocky mantle below.
Which is a problem because you absolutely need the liquid water to physically interact with the rock, to dissolve the minerals and kickstart the chemistry of life.
Exactly. Which leads us to perhaps the most misunderstood planetary feature of all, plate tectonics.
Usually when we hear about tectonic plates shifting, it's on the evening news, and it is bad news. It means earthquakes, tsunamis, volcanic eruptions. It sounds like an entirely destructive force.
It is certainly violent on a local scale, but on a global geological scale, it is the ultimate planetary life support system. Plate tectonics is a massive, incredibly slow recycling engine.
Let's look at the carbon silicate cycle.
When carbon dioxide builds up in the atmosphere, it mixes with rainwater to form a very mild carbonic acid. That acidic rain falls on mountains and weathers the rocks, dissolving the minerals.
The carbon is washed into the rivers, down into the oceans, where marine life eventually uses it to build their calcium carbonate shells.
Right, and when those organisms die, they fall to the ocean floor, locking that carbon away in limestone.
Here is the magic trick of tectonics. The oceanic plates subduct. They literally slide underneath the continental plates, dragging billions of tons of that trapped carbon deep down into the Earth's fiery mantle.
Down there, it is melted, the chemical bonds are broken, and the carbon is eventually vented back out into the atmosphere through volcanic eruptions as fresh CO2.
It is a slow, multi-million-year smart thermostat. If the sun gets too hot, more water evaporates, it rains more, the weathering increases, and more CO2 is pulled out of the air, cooling the planet down.
If the planet gets too cold and freezes over, the weathering stops. But the volcanoes keep erupting, pumping CO2 back into the atmosphere until the greenhouse effect warms the planet back up and melts the ice.
The carbon silicate cycle is brilliant. Tectonics also constantly dredges up vital nutrients from deep underground, like phosphorus and iron, continuously fertilizing the surface for new life.
Without active plate tectonics, a planet's surface would eventually be stripped of the nutrients required for biology. Its atmosphere would stagnate, and its climate would spiral out of control into either a permanent freeze or a runaway greenhouse.
And this is where the statistics start to get incredibly daunting. I was looking at a staggering study from 2024. They ran massive computer models of planetary interiors and crusts to see how common this process is.
Do you remember the number?
Yeah, they found that active continuous plate tectonics might occur on as few as 0.0003% of all rocky planets.
Because it is an incredibly delicate mechanical balance. The crust cannot be too thick or it won't break into plates. It cannot be too thin or it just constantly melts.
The internal heat generation from radioactive decay must be perfectly calibrated.
The mineralogical composition of the mantle has to be just right to allow the rock to flow and bend over long periods.
And crucially, you need liquid water infiltrating the subduction zones to act as a chemical lubricant, physically lowering the melting point of the rock to allow the massive continental plates to slide past and over one another.
Take away any one of those incredibly specific factors, and you end up with what geologists call a stagnant lid planet. A single, solid, unbroken shell of rock completely locked in place. Mars is a stagnant lid. Venus is a stagnant lid.
So we've covered the orbit, the late water delivery, the massive moon, the magnetic dynamo, the gravity sweet spot, and the tectonic thermostat.
Right. Let's zoom into the atmosphere itself, because the air we breathe isn't just a random cloud of gas the planet happened to trap. It is a perfectly balanced, biologically maintained chemical loop.
The atmospheric ratios on Earth are exquisite. You have nitrogen making up about 78%, which is largely inert, providing the bulk pressure and stability so our water doesn't boil.
You have carbon dioxide acting as the critical greenhouse blanket we just discussed, and then you have oxygen at about 21%.
Oxygen is a fascinating problem, though. It's highly reactive. If you just injected a bunch of oxygen into a dead planet's atmosphere, it wouldn't stay there, right?
It would disappear incredibly quickly in geological terms. It would bind with other elements in the rocks and ocean oxidizing them and vanish from the air.
So the only reason we maintain a 21% oxygen atmosphere, which by the way is absolutely vital for the high energy metabolism required to power complex brains and muscles,
Is because it is being continuously manufactured and replenished by biological photosynthesis.
it's an incredible feedback loop. Life creates the very atmosphere that allows more complex life to thrive.
But what's really wild is that this entire process was delayed for eons. Early cyanobacteria were pumping out oxygen in the oceans for over 1 billion years, but the atmosphere didn't become oxygen-rich.
Wait, really? Why?
Because the Earth's crust and oceans were full of chemical sinks, there was massive amounts of unoxidized dissolved iron in the early oceans that just soaked up the oxygen as fast as the bacteria could produce it, literally turning the oceans into rust, which settled on the seafloor.
Only after those chemical sinks were completely filled and saturated could oxygen finally start to build up in the air.
Which brings us to a really fascinating, terrifying constraint on the very building blocks of life itself. Astrobiologists often talk about the acronym CHNOPS: carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur.
These are the fundamental chemical Legos of biology.
But just having those elements somewhere inside the planet isn't enough. They have to be physically accessible on the surface where life can actually use them.
There was a massive 2026 study published in Nature that looked deeply into this. They found an exceptionally narrow chemical Goldilocks zone, specifically for the availability of phosphorus and nitrogen.
This research raises such an important question about the very earliest days of a planet's formation. We have to go back to when the Earth was a magma ocean, when the entire surface was a churning sea of molten rock, and the heavy metals were sinking to the center to form the core.
The 2026 studies show that the ambient levels of oxygen present in that magma ocean dictate where all the other elements end up.
Exactly.
Walk me through that. How does oxygen decide where the phosphorus goes?
It has to do with redox states and chemical affinities. If the early oxygen levels in the magma are even slightly too low, vital nutrients like phosphorus and nitrogen become lithophilic, meaning they chemically prefer to bond with the heavy metals.
So as the iron sinks to form the core, it drags all the phosphorus and nitrogen down with it.
If the oxygen levels are slightly too high, those same elements become highly volatile gases and are lost to space.
That is a phenomenal bottleneck.
Yeah.
You could have a planet with a perfect circular orbit, deep oceans, a massive moon, and active tectonics.
But if the oxygen mixture was off by a tiny fraction during the magma ocean phase 4 billion years ago, all the vital phosphorus is permanently locked thousands of miles deep in the inaccessible metallic core.
The surface is chemically barren. You can't build DNA without phosphorus. You can't build ATP, the energy currency of cells. The planet is dead on arrival.
It all points back to the inescapable concept of sheer, unadulterated luck. Survival is not just about having the right mechanical systems. It is about not rolling snake eyes for billions of years straight.
Speaking of rolling the dice, let's talk about the University of Southampton supercomputer simulation. Researchers there wanted to test exactly how much luck is involved.
Oh, this simulation is wild.
They modeled 100,000 hypothetical planets. They gave every single one of them the perfect starting conditions: water, tectonics, good orbit, and then let the clock run for 3 billion years, subjecting them to random cosmic and geological events.
Supervolcano eruptions, asteroid impacts, solar flares, orbital perturbations.
Do you know how many made it through a 3 billion year run without permanently losing their habitability?
The results of that simulation are incredibly sobering, roughly 9%.
9%. Only 9% of planets that were already perfect candidates managed to stay habitable long enough for complex life to evolve.
Evolution requires incredible luck to dodge fatal cosmic events. Yes, Earth has had horrific mass extinctions. The asteroid that wiped out the dinosaurs 66 million years ago.
The Permian-Triassic dying, often called the Great Dying, where up to 90% of all species perished.
But crucially, we never suffered a total biosphere collapse. Life was battered to the brink, but the unbroken chain somehow survived.
When we synthesize all of this into the rare Earth hypothesis, it becomes clear that it's not just about finding one rare thing. It's about a dozen exceedingly rare things, all happening simultaneously on the exact same rock and maintaining perfect synchronicity for 4 billion years.
Let's do the math that silences the galaxy. Let's actually review these fractions and multiply them together to see what we get. Because this is the moment where the Copernican principle of mediocrity truly falls apart.
Let's run the numbers step by step. First, you need a Sun-like star, a G-type main sequence dwarf. Why? Because the vast majority of stars in our galaxy are M-dwarfs, also known as red dwarfs.
They make up over 70% of all stars. But red dwarfs are deeply problematic for life. They are highly volatile. They frequently spit out massive solar flares that would easily strip a close-orbiting planet's atmosphere.
And because red dwarfs are so much cooler than our sun, their habitable zone is incredibly close to the star. If a planet orbits that close, gravitational tidal forces will cause it to become tidally locked.
Just like our moon always shows the same face to Earth, a tidally locked planet always shows the same face to its star. One side is permanently baking in eternal day, the ocean's boiling, while the other side is frozen in eternal pitch-black night.
That's a nightmare for complex biology.
Yeah.
So we restrict our search to stable G-type stars. That immediately eliminates roughly 90 to 95% of the stars in the Milky Way. We are down to 5%.
Then you need a circular, stable orbit, which we've established is uncommon compared to the highly eccentric orbits we frequently observe.
You need to be in the conservative habitable zone. Based on Kepler telescope data, generous estimates suggest that's maybe 0.37 to 0.60 planets per Sun-like star.
Then we hit the geological and chemical filters. We need active plate tectonics to regulate the climate. According to the 2024 modeling data, that's maybe 0.003% to 0.2% of rocky planets.
Then you need the fractionally large moon to stabilize the axis, which is rare because of the gas drag constraints on larger rocky worlds during formation.
You need the chemical Goldilocks zone for phosphorus and nitrogen in the magma ocean phase, which the 2026 Nature study explicitly called exceptionally narrow.
And finally, you have that 9% chance of dodging fatal sterilizing disasters for 3 billion years.
When you take all those independent probabilities and multiply these fractions together, 0.05 times 0.4 times 0.001 times 0.09, and so on, the cumulative probability drops off an absolute cliff.
The proponents of the rare earth hypothesis estimate that the final product of these factors could easily be 10 to the negative 10 or even 10 to the negative 12.
1 in a trillion.
1 in a trillion. Meaning, statistically speaking, out of the hundreds of billions of stars in the Milky Way galaxy, there may be exactly one Earth-like world capable of supporting a technological civilization.
Or 0. We might truly be the only one.
These numbers completely rewrite how we have to approach the famous Drake equation.
Let's walk through that. Frank Drake formulated his equation in 1961. It has served as the standard theoretical framework for estimating the number of active, communicative alien civilizations in our galaxy.
It's n equals r star, the rate of star formation, times Fp, the fraction of those stars with planets, times Ne, the number of planets that could potentially support life.
Times FL, the fraction where life actually arises, times Fi, the fraction where intelligence develops, times FFC, the fraction that released detectable signals, times L, the length of time they broadcast.
It is an incredibly elegant equation, but proponents of the rare earth hypothesis argue that the way we typically plug numbers into it is dangerously, wildly optimistic.
Specifically, the terms NE, habitable planets, and FI, intelligent life, are often massively overestimated by astronomers who assume habitable just means finding a rock with water in the Goldilocks zone.
Ward and Brownlee argued that we need to aggressively add multiplicative filters to this equation to reflect geological reality.
They propose adding entirely new variables, things like FG, the fraction of stars located in the safe galactic habitable zone, FM, the fraction of planets with a large stabilizing moon, FPT, the fraction with long-lasting plate tectonics.
And there is a brilliant 2024 refinement of this equation by researchers Stern and Garia. They took a brutal, data-driven axe to the FI term, the fraction of life-bearing planets that actually cross the finish line to develop intelligence.
Stern and Garia's work is fascinating. They demonstrated that biological evolution requires environmental pressure to force the development of complex brains, tool use, and adaptability.
They argued that you strictly require the presence of large oceans intermixed with massive dry continents and plate tectonics lasting over 500 million years to continuously change the habitats and drive that evolutionary pressure.
When you require all of that, the FI term plummets. They calculated it drops to a value between 0.003% and 0.2%.
It's an absolute statistical slaughter of our sci-fi dreams. When you incorporate these very real geological and chemical hurdles, the Drake equation violently shifts from predicting a vibrant galaxy bursting with Star Trek-style federations to predicting the Great Silence.
If we pull the lens back even further from our solar system, we have to look at our address not just in terms of our sun, but in the anatomy of the Milky Way galaxy itself. Because real estate matters on a galactic scale, too.
Welcome to the Galactic Habitable Zone, the GHZ, because whole galaxies have Goldilocks zones, just like individual stars do.
And it's basically a massive, ongoing cosmic tug-of-war between two opposing forces, metallicity and radiation.
Let's define metallicity first. In the somewhat quirky language of astronomy, anything heavier than hydrogen and helium is called a metal.
These heavy elements, carbon, oxygen, silicon, iron, gold, are not formed in the Big Bang. They are forged in the nuclear hearts of massive stars and blasted out into space by supernova explosions.
You absolutely need these metals to build rocky planets. If you don't have enough metals in the local stellar nebula, gravity can only form massive gas giants or tiny, useless clumps of ice.
So, if we need metals, where are they all located? They are concentrated heavily in the inner core of the galaxy, near the center, where star density is highest, stars live fast and die young, and supernovae are constantly going off, enriching the surrounding space.
But there is a lethal, devastating trade-off to living downtown. The inner core is incredibly metal-rich, but it is an absolute war zone of ionizing radiation.
You have frequent supernovae, massive gamma ray bursts, and the violent, unpredictable activity of the supermassive black hole at the center of the Milky Way, Sagittarius A star.
If a rocky planet somehow manages to form there, the ambient radiation is so extreme that complex life would be sterilized on the surface faster than it could ever evolve.
Plus, the stars in the galactic core are packed so tightly together that their gravitational fields constantly perturb each other's outer systems.
This is a major factor. Every star likely has an Oort cloud, a massive, loosely bound spherical shell of billions of icy comets orbiting far out in the deep freeze of the system.
In the dense galactic core, passing stars regularly drift too close to one another. Their gravity disrupts those delicate Oort clouds, sending a relentless, inescapable bombardment of comets raining down on the inner planets.
You would have dinosaur killer extinction level impacts every few million years. You can't build a civilization under that kind of artillery fire.
The inner core is out, lots of building materials, but you get fried by gamma rays and pummeled by comets. Result, dead rocks or highly irradiated hot Jupiters.
Okay, what about the exact opposite? What about moving out to the far outer rim of the galaxy, far away from the chaos?
The outer rim solves the radiation problem. It's very quiet, very safe. But the star density out there is so incredibly sparse that there simply haven't been enough generations of supernovae to enrich the area with heavy elements.
The metallicity is far too low. You literally do not have the physical iron and silicon required to build an Earth-sized rocky planet out there.
You can't be too deep in the violent city center, and you can't be too far out in the resource-poor rural void. You have to live in the quiet, well-supplied suburbs, and that is exactly where we are. Earth is located about 26,000 light-years from the galactic center, in a minor spur called the Orion Arm.
It is the perfect galactic address. We are just close enough to the center to have the required metallicity to build a large, rocky world with a heavy iron core, but we are far enough away to avoid the lethal radiation and gravitational chaos of the densely packed inner galaxy.
There is another incredible detail about our address. Our sun has a nearly circular orbit around the galactic center. Why does that matter?
The Milky Way is a spiral galaxy. It has massive spiral arms. These are incredibly dense regions of active star formation, super hot young stars, and frequent supernovae.
Because our galactic orbit is circular and moves at roughly the same rotational speed as the spiral arms themselves, we mostly stay out of them. We cruise comfortably in the safe, quiet, empty gaps between the arms.
I say mostly, because there is a deeply fascinating theory being explored by paleontologists and astronomers. It suggests our sun's orbit isn't perfectly matched to the arms forever, and we do occasionally drift through the denser edges of a spiral arm, roughly once every 100 million years or so.
And when we do cross into those denser galactic regions, our solar system gets exposed to higher ambient radiation and gravitational nudges to our own Oort cloud comets.
Some geologists have looked deeply at the fossil record and found a potential statistical correlation between those 100 million year spiral arm crossings and Earth's major mass extinction events. Our galactic weather literally shapes our biological evolutionary history.
It's a breathtaking connection. The slow rotation of the Milky Way galaxy dictating the survival or destruction of specific species on a tiny rocky crust 26,000 light years from the center.
We have built a very intimidating, highly detailed case for Earth being a 1 in a trillion freak of nature. But to be intellectually fair, we have to look at the pushback.
Mainstream astrobiologists do not just roll over and accept the rare Earth hypothesis without a fight. There are highly credible, rigorous counter-arguments that we need to explore.
The single most potent counter-argument is simply the law of large numbers. Human brains are notoriously, comically bad at comprehending the true mathematical scale of the universe.
I'll play devil's advocate here. Sure, all these chemical and orbital bottlenecks sound impossible. Maybe the odds really are 1 in a trillion. But we are talking about an observable universe with an estimated 10 to the 22nd to 10 to the 24th stars.
That is a 1 with 24 zeros behind it. When you have a sample size that massive, even an impossibly rare event, something with a 1 in a trillion chance is mathematically guaranteed to happen billions of times across the cosmos.
And we don't even have to look at the whole universe. Even within our own Milky Way, observational data actively pushes back against the rare Earth pessimism.
The Kepler Space Telescope spent years staring unblinkingly at a tiny, specific patch of the sky, meticulously looking for the incredibly faint dimming of starlight as exoplanets transited in front of their host stars.
Based on extrapolations from that Kepler data, astronomers estimate that roughly 1/5 of all sun-like stars host Earth-sized planets in their respective habitable zones.
1/5. If you run that math out across the galaxy, that yields roughly 8.8 billion potential Earth-sized candidates sitting in habitable zones in the Milky Way alone.
The proponents of a crowded universe look at those 8.8 billion candidate worlds and say, you are seriously telling me not one of them rolled the right combination of orbital, geological, and chemical dice.
Another major critique leveled at rare Earth is that it is incredibly, almost arrogantly Earth-centric. It assumes that all complex life everywhere must follow the exact same biological and chemical pathway that we did.
It assumes life must be carbon-based, water-dependent, oxygen-breathing, and live on the rocky surface of a planet under an open sky.
The discovery of extremophiles severely weakened that Earth-centric bias. We found vibrant biology thriving in conditions we previously thought were universally lethal to all chemistry.
If life is fundamentally that resilient and creative, then our definition of what constitutes a habitable environment is likely far too narrow.
What if you don't even need a surface? Look at the icy moons right here in our own outer solar system. Take Europa orbiting Jupiter or Enceladus orbiting Saturn.
They are hundreds of millions of miles outside the traditional Goldilocks zone. The ambient temperature is hundreds of degrees below zero. Their surfaces are frozen solid.
But underneath, miles of thick ice. The gravitational tidal heating caused by the massive pull of the gas giants generates internal friction. That heat keeps a massive global ocean of liquid water sloshing around in the dark.
That miles-thick ice shell acts as a perfect, impenetrable shield against cosmic radiation and solar flares, completely upending the need for a planetary magnetic field or a thick atmospheric blanket.
You could theoretically have incredibly complex alien ecosystems flourishing in the pitch-black subterranean oceans of rogue planets, drifting completely starless through interstellar space, warmed entirely by internal tectonic friction and shielded by ice.
Which means there could be billions of viable habitats out there that don't look anything like Earth. And then there is the actual real-time observational data we are getting right now from the James Webb Space Telescope.
JWST is so powerful it is actively peering into the atmospheres of distant exoplanets to see what they are made of. In 2025, researchers confirmed the existence of super-Earths like HD 2794d and GJ 251c sitting right inside their stars' habitable zones.
It is a remarkable time for astronomy. Now, to be fair to the rare Earth camp, JWST also found that TRAPPIST-1d, which was considered a major Earth-sized candidate, seems to completely lack a thick atmosphere, likely stripped away by its red dwarf star.
That was a big point for the rare Earth argument. But the search for atmospheric biosignatures, detecting specific ratios of gases like methane and oxygen coexisting in a state of chemical disequilibrium that strongly implies active biology, is just in its absolute infancy.
The moment JWST, or a future observatory, detects a confirmed, undeniable biosignature on just one other world, the rare Earth argument shatters entirely.
If we find life twice in just our own tiny galactic neighborhood, the mathematical implication is that the universe is absolutely crawling with it.
But until we actually find that second data point, we are fundamentally trapped by what statisticians call the Bayesian N1 problem.
Let's talk about David Kipping. He's an astronomer who ran a brilliant Bayesian statistical analysis on this exact problem. The core issue is that our sample size for life in the universe is exactly one: us, Earth.
Trying to extrapolate sweeping statistical probabilities about billions of galaxies from a single data point is notoriously dangerous math.
Kipping applied Bayesian inference, which is a method of updating probabilities as you get more evidence, to the timeline of Earth's history.
He noted that basic microbial life emerged here almost immediately after the early oceans cooled down, roughly 3.8 billion years ago. The moment the planet was physically capable of supporting life, life was there.
But intelligence, technological, communicative intelligence, took nearly the entire 4 billion years of the planet's habitable window to show up.
Using that specific timeline as the data point, Kipping's Bayesian modeling found a 9.1 odds that the emergence of basic life is a rapid, common, nearly inevitable process on habitable worlds.
But crucially, he found 3.2 odds against the rapid emergence of intelligence.
To summarize Kipping's highly complex mathematical finding, maybe Earth isn't rare at the starting line of the evolutionary race. The universe might very well be full of microbial oceans and cosmic mold.
But Earth is profoundly, exceptionally rare at the finish line. The hurdles required to reach intelligence are just too high, the timeline is too long, and most planets simply stumble and fail before they get there.
This brings us to a philosophical trap that is so hard to wrap your head around, but it is the absolute crux of the entire debate. It is called the anthropic blind spot.
The anthropic principle, addresses a fundamental, inescapable bias in how we observe the universe.
The weak anthropic principle, or WA, simply states that the physical conditions of the universe we observe must, by definition, be compatible with the existence of observers. Because if they weren't, we wouldn't be here to observe them.
I love the analogy for this. It is exactly like interviewing the sole winner of the mega lottery. You put a microphone in their face and ask, hey, is buying a lottery ticket a solid financial investment?
And the winner enthusiastically says, absolutely, it's guaranteed. I bought one ticket and won $200 million. It's foolproof.
The winner is entirely blind to the 50 million people who bought tickets and lost everything, because the losers aren't the ones giving the interview.
We are the cosmic lottery winners. We look around at our solar system and say, wow, what are the odds that we happen to have a large, stabilizing moon, a highly active geodynamo, perfect plate tectonics, and a gas giant like Jupiter sweeping up dangerous asteroids for us?
The weak anthropic principle reminds us, of course we see all those things. If we didn't have every single one of those perfect conditions, we wouldn't exist to have this conversation.
We would just be dead rock or mold in a basement.
We cannot objectively measure how mathematically rare our planet is, because the very fact that we are alive and capable of measuring it requires the planet to be completely perfect. Our very existence makes us inherently biased judges.
Some theoretical physicists take this even further to the strong anthropic principle, or SAP. This is a highly controversial, somewhat teleological idea that suggests the universe must possess properties that inevitably allow life to develop at some stage.
Many scientists reject the SAP because it borders on the philosophical or mystical, implying the universe was somehow designed with a purpose or an inevitability toward consciousness.
But regardless of how you feel about the strong version, the weak anthropic principle provides a sobering reality check on our optimism. It means we might be staring out into a galaxy full of dead, sterile rocks, entirely oblivious to our own ridiculous, improbable luck, naively assuming everyone else out there has a moon and a magnetic field, too.
We have to consciously navigate this anthropic bias. The fact that we are the final product of a 4 billion year success story makes us incredibly poor judges of how common that story truly is.
This leaves us with a massive, weighty synthesis to consider. We have explored the terrifying, shifting gauntlet of the continuously habitable zone.
We've broken down the simultaneous planetary engines, from the Theia impact forming the moon, to the magma ocean oxygen levels dictating phosphorus, to the carbon silicate thermostat.
We've done the brutal multiplication of the Drake equation filters and mapped the quiet suburbs of the galactic habitable zone.
The ultimate question remains. If the rare Earth hypothesis is, in fact, the closest model to reality, what does it mean for us?
Scientifically, it perfectly, chillingly resolves the Fermi paradox. The great silence we hear when we point our telescopes at the stars isn't because aliens are intentionally hiding from us in some prime directive scenario.
It's not because they are using advanced communication technology we can't detect. It's because they simply aren't there. The stage is empty.
It forces us to confront the concept of the great filter. This was proposed as an unseen evolutionary or catastrophic barrier that prevents ordinary matter from undergoing the full, uninterrupted journey from dead chemistry to an expanding interstellar galactic civilization.
The terrifying question in astrobiology is always, is the great filter ahead of us, or is it behind us? If the filter's still ahead of us, perhaps in the form of rogue artificial intelligence, inevitable nuclear war, or catastrophic ecological collapse, then we are doomed to hit the same wall everyone else did.
But if the rare Earth hypothesis is right, the great filter is safely behind us. The filter was the incredibly improbable jump to metazoan complexity.
The filter was surviving the magma ocean with the right chemical elements available. The filter was getting hit by Theia to form the moon without destroying the planet entirely.
If that is true, humanity is unbelievably, astronomically lucky. We made it through the impossibly tight bottleneck that caught almost everyone else.
That realization, the reality of a lonely, statistically miraculous Earth, elevates the intrinsic value of our planet to an almost incomprehensible level.
This is where the hard science hits the soul. Think about it. If the principle of mediocrity was right, and there are millions of thriving Earths out there, then, well, our Earth is just a franchise, a cosmic Starbucks.
If we mess this one up, if we destroy our biosphere, the universe carries on. Biology continues elsewhere.
But if we are an anomaly, then the Earth is not just our home. It is the most precious, delicate, irreplaceable object in the entire known universe.
It creates a staggering, unprecedented ethical mandate for our species. A self-inflicted ecological collapse isn't just a local disaster. It's not just a political or economic failure.
It is a profound cosmic tragedy. Extinguishing the biosphere of Earth might mean permanently extinguishing the only spark of complex intelligence in the Milky Way.
We hold the absolute monopoly on consciousness.
If we are truly alone, the universe's ability to know itself, to observe its own stars, to understand its own quantum physics, to create art, to compose mathematics, rests entirely precariously on human shoulders.
There is no backup civilization waiting in the wings to carry the torch. There is no benevolent galactic federation coming to step in and save us from ourselves.
Before we go, I want to leave you with one final provocative thought that builds on everything we've just discussed. If the rare Earth framework is right, and it truly takes 4 billion years of perfect, unbroken luck to cross the finish line to intelligence, maybe we aren't late to a galactic party that has already died out.
That is a profound flip of the perspective.
What if we are just the very first to arrive? Someone has to be first. If we are the single success story of the early universe, that means we might be the ancient, mythical, precursor alien race that future galaxies will one day search for.
Millions of years from now, newly evolved civilizations on distant worlds might look up at the stars, wondering where everybody is, completely unaware that we are the ancient ancestors who seeded the galaxy. We aren't late to the cosmic party. We might be the ones hosting it.
So the next time you walk outside on a clear, dark night, the next time you look up at that massive dusting of stars and feel the sheer, crushing weight of the great silence, don't feel small. Don't feel insignificant.
Look down at the dirt, breathe in the biologically forged oxygen, and realize that you are standing on a statistical miracle. You are the product of a 4 billion year unbroken chain of impossible luck. The universe has given us the rarest of gifts. What are we going to do with it?
That is the ultimate question of the great silence.
Thank you for joining us for this edition of Audio Notebook. Keep looking up and keep asking questions.